Hello, this is the Chapter 1 slides from the Solomon's 12th edition. We're going to be going in and talking about structure and bonding and what is organic chemistry and how the atoms go together. But first off, so what is organic chemistry? It's really about what you can do with carbon. Carbon has some very unique properties because it can make quite readily single bonds, double bonds, triple bonds, and bond with a lot of other different elements, stuff like that. So it's mainly covalent and polar covalent bonds, which we'll talk about in a minute. And and in reality, what it does is it forms the basis of life on this planet, stuff like that. And so really what organic chemistry is about is sort of how do you manipulate those carbon-based compounds? How do you detect them? How do you build them? And figuring out how they work in life, stuff like that. And so, there's a vast array of organic compounds that you deal with throughout your lives, whether they be pharmaceuticals, like so this one here, this is atorvastatin. It's Lipitor it's used for cholesterol lowering, stuff like that. You can do any of the polymers. So this particular one is nylon 6,6. So there's two components that go together to make in a long chain to make the polymer, stuff like that. So cotton, stuff like that. So and different fabrics. So not only just cotton, but also if you think about the special fabric that was developed by Under Armour to wick away the sweat to cool down athletes. So that was all developed by chemists. You can also think of the dyes. So this is one of the red dyes, and being able to develop dyes that when you wash the clothes, they don't fade or turn everything else in your washing machine pink, stuff like that, as well as nutrition. It forms the basis of life, and so these are the components that you that you consume, stuff like that. So this one here, this happens to be riboflavin. So this is actually a flavin molecule here bonded to a ribose. So that's the name. Okay, so atomic structure, just for the basics. In the nucleus on the inside, you've got the protons, which provide, which define the atom. So all carbon atoms are going to have 6 protons. All hydrogen atoms have 1 proton. All helium have 2. So like that. So the neutrons are also in there. That stabilizes the nucleus. It provides bulk and stability. And then electrons, which have negative charges, are going to be whirling around the outside. And those are gained or lost to perform chemistry. Like that. And so you can have different isotopes. So that's specifically varying the number of neutrons. So like that. So all carbons have 6 protons. That's by definition. If you have 6 protons in your nucleus, you are a carbon. But you can have different levels of neutrons. So by that. So carbon 12. So with that, atomic mass 6,6, 12. You have 13 and 14. These are the common ones. I think there's also an 11. Like that, but they all still function as carbons. So with that, with the electrons, the important ones are the valence electrons. Those are the ones that are most likely to be gained or lost. With that, and you want to get them so that they can get the same number as the nearest lone pair, or the noble gas, which is right here, helium. So if helium gains 1, it can have its electrons look like helium. But lithium, the easiest way to do that is to lose 1 to become helium, lose an electron, and so it would have a plus charge. To figure out how many of these valence electrons you have, you can just count over. So lithium has 1, beryllium 2, 3, 4, 5, 6, 7, 8. Now when you get down here, you just kind of skip over the transition metals. So you would count 1, 2, 3, 4, 5, 6, 7, 8. Sometimes you'll actually see, like this one here, you'll actually see like 1A, 2A, 3A, 4A, something like that. So that actually tells you directly how many valence electrons there are. So again, there's the way that chemistry works is that atoms will either share or exchange electrons in order to get into this noble gas configuration. So with an ionic bond, what you're doing is you're actually one atom is giving its electrons completely to the other atom, and so they would both have their test. So the classic one is sodium chloride. So sodium, it'll give an when it gives up one of its electrons, it'll turn into neon. If it gives it to chlorine, then chlorine can then gain another electron and then have the same electron configuration of argon. And so they're both going to be in their ideal situation, and this one would have 8 with that, and the chlorine would have 18. So with that, so this would have 10. This would have 18. Which is exactly what they want to do. So with covalent bonds, what you're doing is there's not this pull, so with that, and so what they're doing is they're sharing electrons, and by sharing, they can get to their noble gas configuration for their electrons. Okay, so again, for like this here, you've got one electron flying over, and so now the lithium has 3 protons, 2 electrons, so it's 3 positive charges and 2 negative charges, so it has an overall plus charge. Here, the fluorine has 9, so with that 9 protons, but 10 electrons, and so now it has 1 more electron, so it has a negative charge. With that, so you can have the pull of atoms to a pull of electrons to an atom is different from each one, and that's constituted as electronegativity. And so you can look on the periodic table. You're not counting the noble gases. The fluorine is the most electronegative because it's small. It doesn't have a whole lot of electron density flying around outside, sort of to smother the pull of the electron or of the nucleus. So it pulls really tightly. Chlorine, bromine, they're still very electronegative, stuff like that, but they're much larger. They have a lot more insulation, a lot more electrons in their core, and so the outer valence electrons aren't feeling the nucleus nearly as much. So that lowers the electronegativity. But on the periodic table, the closer you are to fluorine, the more electronegative you are. Okay, so covalent bonds is usually, so you have H2, that's the simplest of the covalent compounds, right? Each one is going to contribute an electron, so they come together. Each bond is 2 electrons, but it's usually written like this. But each bond is representative of 2 electrons, and so since they're both sharing it, this one looks like helium, this one looks like helium, and that's good enough. So for Lewis structures, so what you do is you replace the 2 electron dots of the bond with a dash, stuff like that. And so here, so you have chlorine, so you have these 7 valence electrons and these valence electrons. These 2 single electrons come together to make a bond. Now, lone pairs you still write, but the bond itself can just be just a dash. So for that, you can also do double bonds, right? So when there's 4 electrons, 1, 2 bonds. Triple bonds, 1, 2, 3. But again, the lone pairs are still shown. Okay, so for Lewis structure, it's not actually at the end of the slide deck. It's actually in Blackboard. I posted some slides. So with that, if you want to go back and take a look at how you draw Lewis structures. So there are some exceptions to the octet rule. One being hydrogen, it only really needs 2 electrons because it can turn into helium, stuff like that. So really, it only wants 1 bond. The other one's in the 3rd row or after, so phosphorus, sulfur, chlorine, and those below it, they have access to d orbitals, so they can actually throw in more. So if you have phosphorus pentachloride or sulfur hexafluoride, here they've got 5 bonds. This actually technically has 10 valence electrons, 5 bonds. This has 6 bonds, stuff like that. So that's fine. It gets a little weird. But if you're up carbon, nitrogen, oxygen, fluorine, those can only have 8 electrons in them, the valence electrons. So formal charge. So this is a way of keeping track of how electrons are gained and lost. And so you've probably been introduced to this in general chemistry about charges, stuff like that. So it's a little bit different the way you do that with organic compounds, but it's essentially saying the same thing. But because we're dealing with mostly covalent bonds, it becomes a little bit issue, stuff like that. So the way that you can do this, so if there's a net loss of electrons, right? You have fewer electrons than protons, and so it'll be plus charge. But if you have a net gain of electrons, that would give you a negative charge, right? Because now you got an excess of negative charges. So by that, so the how you do that is you count how many. You start from where the atom was, how many valence electrons it has, and then it subtracts the valence electrons in the molecule. So how many does it have now? So what it started with on the periodic table minus what it has now. Now when you have a bond, what you do is you split it evenly. So one electron from the bond goes to one atom, and the other goes to the other. Lone pairs just stay with whatever atom they were on. Okay, and so if you have ammonium here. Right, so remember each one of these bonds is 2 electrons. So I usually just put dots on either side of the bond. So by that, so you're going to slice these. Right, so each hydrogen is going to look like this, and the nitrogen is going to look like that. Okay, and so hydrogen starts off with 1 valence electrons. It has 1 electron now, and so it has charge of 0. Nitrogen normally has 5 electrons, but now it only has 4, right? So now the charge is +1, and so how we would write this is usually put the charge next to the atom that needs it, and so it ends up going like that. Okay, so if you're looking at these, right? So you got formate here. Okay, so we're interested in in that oxygen, right? So we're going to slice this. I'm going to put in dots for those electrons. So if you slice that, right? So these are going to be the lone pairs, right? And then you had 1 electron from each one of those bonds, and so it ends up being, you start off with 6 because you've counted over oxygens. It ends up being 6. It's got 6 now, right? So it's 0. Put that carbon there. Right? You got 1 from each one of these bonds, 1 from this bond, 1 from that bond. So it starts off with 4, and then you subtract the 4 it has now, right? 1, 2, 3, 4. So that is also 0. Okay. The hydrogen, right? It looks like this, right? Just 1 from this one, 1 from that bond, I should say. You know, it starts off with 1, it has 1 now, so that's 0. And then this one. Right, so we have 3 sets of lone pairs, and then we've got one electron from this bond, so it ends up being that. And so the oxygen, right, normally starts off with 6 in the periodic table, but now it has 1, 2, 3, 4, 5, 6, 7, and so 7, so it's -1. Right, so there is in fact a -1 charge there. Okay. Okay, so this is a nice little summary for it. So like that, and so if you want to be able to figure this out, so that you can actually look at the periodic table, and this works on each one of the columns. So if you don't want to look at carbon, nitrogen, oxygen, fluorine, neon. Okay, so if you count over, so the way that I usually do this, so you want to look at lone pairs and electrons. And bonds at once. Okay, so carbon has 4 valence electrons, and so what you do, and we'll talk about this in a second, they actually like to be singles 1, 2, 3, 4 before they pair up. So 1, 2, 3, 4. So it has 4 electrons that are looking for bonds, right? So it doesn't have any lone pairs, but it really wants to have 1, 2, 3, 4 bonds. Okay, for nitrogen it has 5 valence electrons, so 1, 2, 3, 4, 5. So it has 1 set of lone pair, and then it really wants 3 bonds. So 3. Oxygen, it has 1, 2, 3, 4, 5, 6, right? So it has 2 lone pairs, and then it wants 2 bonds. Fluorine has 7, so 1, 2, 3, 4, 5, 6, 7. So it has 3 lone pairs, and it wants 1 bond. Right? And then neon has 8, so 1, 2, 3, 4, 5, 6, 7, 8. So it has 4 lone pairs, no bonds. Okay, and so wherever you have a single bond here, or a single electron, that's where you're going to want a bond. But if this is what the atoms really want to have. if it's anything other than this, even though the octet is filled, if it's filled up any other way, there's going to be a charge associated. So let's say it's got, so here the carbon only has 3 bonds, so it has a plus charge. Here the nitrogen, right, it has, in here the nitrogen has these 4 bonds, so it has its electrons, or it has its octet filled, but it doesn't have the lone pair that it really wants. It really just has 4 bonds. Same thing here. If the octet is filled, but again, it really wants to have that second set of lone pair instead of the third bond, so it has a positive charge, and the opposite, right? So with that, all of these have their octet filled, but that's not how it normally would want to be. So that's where they get the charge from. Okay, so for isomers, this just means that they have the exact same formula. So in this case, in these two, it'd be C2H6O. So by that, but they are completely different structures. So this one here, right? So here you've got carbon, oxygen, carbon. Here you've got carbon, carbon, oxygen. So ethanol and dimethyl ether are completely different. So if you if you inhaled this one, this used to be used as a for anesthesia. With that, and this one here used to be obviously it's the alcohol that we drink. So 2 totally different compounds, but they have the same formula. Okay, and so what we can do is we can say, okay, draw these, right? So by that, and so what you can do is you can, when I typically draw, so let's say I said C3H8O, right? So, but let's say well, let's do so with that. So we'll get this closer when we get functional group. So an alcohol, which is actually an OH, which you'll learn in next chapter. So when you usually draw these, put these together as single bonds, right? So with that, so let's say, I want the OH here. So then you can then fill in the rest of the 4 bonds that carbon wants with hydrogens. So that's usually what we do. Just go ahead and draw in the carbons, put in your functional group, fill in with hydrogens. Okay, so for drawing structures, there's 2 primary ways that I'm going to draw these, and unless the question on the test specifically asks it, which it will on the first test, but after that I don't care. You can use either what's called a condensed structure or a skeletal structure, which is the book calls a bond line formula. So like that. So you can use either one, and actually it's sometimes good to mix and match, because this will show you all the atoms. The skeletal structure, which we'll talk about in a few minutes, is much simpler. But there's benefits to both, and you'll see me even in some molecules use both. But going forward, unless I asked you specifically which version I want, I don't care. Stuff like that. And so what's happening is, so you assume that the carbons, if you don't see a bond, you assume that they are single bonds. Now, if they're double or triple bonds, then you actually have to draw those in. So, like, let's say there's a double bond here, you'd actually draw that in. Stuff like that. But what it's saying here is that the atoms that are after this carbon, all of these are attached to there. Okay, all those are attached there. All those are attached there. These hydrogens, they're attached to that nitrogen, and this group here is attached to that carbon. Now, sometimes what you can do is you can put parentheses around here. So with that, so if you have a group coming off of the main chain here, you can draw a bond to it, and then just continue that chain in here, right? So these 2 are right there. Those 3 hydrogens are there. So you can do that. So with that, the other way that you could do this is put this in a parentheses and put it down here. So I like parentheses. So for this one, so C. Okay, so okay, so this one. Okay, so yeah, you can see how much how tedious this can become if you have to draw on every single bond. Okay, so let's start with just this longest carbon chain here. So C, 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 C. We're going to assume that everything is a single bond. So we're not actually going to draw any bonds. So you can either do one of 2 ways. You can either say, okay, these guys here, right? They're going to be on here, right? So we're going to just write it CH3. Here, well, we're going to skip this one, but here it's got these 2 hydrogens here, right? You can assume that since the carbons are on either side, that they're also bonded to it. These 2 hydrogens here are bonded to it. You can assume these 2 carbon-carbons are bonds, so indicate those. So CH2, and here it's these CH3, and we can assume this bond is going to there. Now this one, you have a CH. You can either do it one or two ways. You can either put a line up here and then go CH3, right? So to denote these three are on that carbon. And so there you go. You can compress it if you want, but that's fine. The other way that you could do it is CH3, CH, CH3, CH2, CH2, CH3. And what this is saying is that this CH3 group is on that carbon there. Okay? So that the parentheses mean everything that's in there is bonded to that. So I'll take either one, just whichever one you're comfortable with. So for skeletal structures, these are the structures you actually saw on the very first slide. So this is a way where we can get away with not drawing all the carbons, all the carbon bonds and CH bonds. Okay, so where two lines intersect, or at the end of a line that doesn't end in a different atom, we assume that is a carbon. So I'm a big proponent of putting dots wherever the carbons are, and I think that works out well when you're first starting out. Stuff like that. So one nice thing is you do not need to draw in any CH bonds. Now, if the hydrogen is on anything else, you have to draw the hydrogen, either as a line, either with an actual line, or just like a condensed structure. But what you can do is you can say, okay, this particular carbon, I only see, let's say, 3 bonds. That means the fourth bond that's not explicitly drawn is a CH bond. If a bond has, say, if I only see two bonds off of it, we can assume that the other two are hydrogens. Now, if there's a charge, then it becomes a little more complicated. But for things that are not charged, you can always just assume that there's 4 bonds. Never any more than that. Okay, and so this is the Lewis type structure. It's also called a Kekulé structure. So for that, and so the skeletal structure will be like this. And notice how the double bonds are shown. But down here, right, there's an OH right here. So by that, so that H is shown, but none of these hydrogens here are shown. Okay, none of these hydrogens have to be shown. So there is a carbon at this end because it doesn't end in a different atom. Here you have a carbon here, and it goes to that oxygen there. There's no like carbon in between. It goes from this carbon here up to there. But here you go from this carbon, and then there's actually there's a carbon here because another bond isn't shown. But there's only one bond shown for this carbon, so that means the other 3 bonds that carbon needs are hydrogen. So it's 1, 2, 3, like this. Okay. Sometimes you will see me invert the order. And what this is doing is it's saying, so you'll see me write it like this. And what it's trying to do is explicitly show that it's like in this case it's a carbon-oxygen bond or a carbon-carbon bond. If I were to write it like this, if you write it like that, that's fine. But what you have to know is that it's like that. Okay, so that there's actually a carbon-carbon bond there, and it's not CH, or CH, and then another carbon here. Okay, it's not this. It isn't. So none of those will work. It's actually like this. So carbon-carbon, and this carbon has 3 hydrogens hanging off of it. Okay, so sometimes it's inverted in order to be able to make sure that it's clear. But if it's pretty much if it's just one little group hanging off, we can invert it. If it's a big group, then we'll just write it as normal, and you just have to know. Okay, so for skeletal structures, let me go ahead and draw this out. Oop. Don't need that. Okay, so the first thing that you can do is get rid of any of the H's. Just don't even worry about them. Okay, so we don't worry about that one. Don't worry about this one. Now these 2 hydrogens, you can't get rid of them because they're bonded to a nitrogen. Okay. The next thing to do is put in dots, sort of sketch out where the carbons are, but just in dots. This, carbon, carbon, carbon. This one, and then you can fill in the bond, sort of connect the dots like that. There's a double bond here, right, so you have to put 2 lines. Single bond, double bond, okay. And then that nitrogen, so NH2. So you can do either, you could either put the group like this, or you could write it NH2. It doesn't matter. I'd go ahead and put in the lone pairs. Just get in the habit of putting in lone pairs. I usually don't count off for it unless I specifically ask for it. But it's a good habit to get into because we're going to be using these lone pairs later on. So and then you don't forget the fluorine and its lone pairs, and that's it. So that's your skeletal structure. So with that, so each one of these dots is a carbon. So with that, and if it's not a carbon or it's a CH bond, then we have to show it specifically. Okay. But I would recommend using the dots to start off with. I sometimes still use them. Okay, and so one of the problems with drawing these on paper is that, you know, we live in a, you know, we perceive in 3 dimensions, and with that, so most things we interact with are 3-dimensional. So how do we show that in a 2-dimensional picture like this? And so the way that we do that is we said, okay, so let's say this is in the plane of the, let's say this bond is in the plane of the board. If we want to represent an atom coming out at us, so with that, and so like this one here, notice how it's pointing towards us. What we do is we do a heavy line, so we sometimes call it a wedge. So with that, so a heavy line, that means it's coming out towards you. If, you know, like this one here, it's going away. So how do we represent that? Well, that's, we usually consider that to be, we use a dashed line. So with that, so with that, so dashed line there, that represents a bond that's going away from you. It's going away from the paper, away from the board. With that, so just be aware. Okay, so for 3-dimensional structures, right? So with that, so this hydrogen's coming out at you, away. That's in the plane. This is in the plane, and you can rotate these around. You know, they're going to be tumbling in space. You're actually going to get rotation. We'll talk about that in a minute. So with that, and so be aware. So with that, so you can have this, right? So you can have double bonds, triple bonds, right? So for triple bonds, lots of times, so don't forget that there's, you know, you're going to have a carbon, you know, so let's say, so don't forget that this is, and then, right, there's only, on that particular carbon, there's only 3 shown, so there's actually is a hydrogen there. Lots of times what you'll do is you'll see me draw it like this. It's actually better to have it drawn like this because that's more accurate, because there actually is 180 degrees around this bond, but just for simplicity's sake, so you can see, it's a little bit easier to see that it's a triple bond, that there is a carbon here. I'll sometimes draw it with a kink. So just be aware that that's actually not true. It's actually 100. There's actually 180 degrees in here, not 120. So with that, but just for simplicity. Okay. So the next concept is what's called resonance structure. Now this is weird. It's not hard, but it's just one of the sort of weirder things. The problem is, so Gilbert Lewis developed these, developed Lewis structures, and they've worked phenomenally well for the last 100 or so years. But there is in fact a problem. And so the Lewis structure works so well that what we do is we sort of have a workaround to solve the problem. Okay, and so what happened is, so let's say you look at, this is acetate. Okay, so if you look at carbon oxygen double bonds, right? So in a bunch of different molecules, they're about 120 picometers long. Okay, if you look at carbon oxygen bonds, the typical one's about 135 picometers. But when you look at the actual acetate, when you measure these carbon oxygen bonds, they're both the same, right? There's 127 picometers, or in fact, they're both what is essentially a 1.5 bond length, stuff like that. And so what's really happening is we can draw the structure like this, and we can draw the structure like this, and those are equally valid. And so really the resonance, what's the actual situation is, it's in fact smeared, you know, you've got half a bond that's kind of smeared between these two, right? So, or a bond that's smeared between the two, so they're like a half a bond with the negative charge in the middle. Stuff like that. But the problem is this is hard to write and it's hard to interpret, and so we usually just draw it like this and recognize that, yep, we can have a resonance structure where sometimes it's like this, half the time it's like this, half the time it's like that. stuff like that. And so what's happening is you can, we have to take that into account, stuff like that. And so when you draw a Lewis structure, a resonance structure, it still has to be a valid Lewis structure. You can't give carbon 5 bonds. You can't do all sorts of wild and crazy things, stuff like that. So, but the other thing is, it's just electrons moving. There's no atoms that move. If an atom moves, then it's a completely different structure. It's not a resonance. Here it's just atoms, or it's just electrons, right? So this lone pair can come down to make a double bond, or to make a second bond, right? So, but that's the same thing here. This set of lone pair electrons can come down. There's 2 electrons. You can make another bond there, stuff like that. And so it's just electrons moving. There's no atoms that move. So rule 2 is the fact that if you, it's the resonant hybrid is really the true structure. So by that, and so if you're looking at a duck-billed platypus, okay, sometimes it's good to talk about the duck properties. Sometimes it's better to think about it as the otter properties, stuff like that. And so sometimes it's better to just, for simplicity's sake, think of a duck-billed platypus as just a duck, stuff like that. So, but just keep in the back of your mind, it's really just a platypus, and so we're just using it for simplicity's sake. So just be careful, stuff like that. So these are the sort of requirements. The more requirements that these fill, the more important that resonance structure. Okay, so so not all resonance structures are equal. So some are going to be represented more, some are going to be more important than others. Right, so with that, for example, so the 3 of the rules are the greatest number of atoms with their filled octets. Okay, and so like here. So with that, so this carbon here doesn't have its octet filled because it only has 3 bonds. Okay, so the most covalent bonds, right? So with that, and so this one has 1. If you just look at these inner bonds here, 1, 2, 3, 4. This one only has 3. So with that, and then the fewest number of atoms with a formal charge. Well, they both have an atom that has a formal charge. Sometimes you can't get away from it. Sometimes you can't get away from it. So with that, but it's better to have 1 atom in the molecule have a charge as opposed to like 3. So with that, and so which resonance structure is more stable, which is more important? Like we said, this one doesn't have its octet filled, so with that, but this one it does, right? So this carbon has 1, 2, 3, 4 bonds, right? This oxygen has its 8 electrons around it, 3 bonds and a lone pair. So this one has all its octets, octets for all the carbons filled, and so in fact this is the more stable of the 2. Okay, so the other thing is this resonance provides stability. The more, in a way, what's happening is, so if you have a charge, more atoms are bearing the weight of that charge. Okay, so by that, so in here you've got 2, you have 2 oxygens, bearing that negative charge, something like that. And so I always think of it as like a 100-pound couch that you need moved. If you're going to move it, it's going to be really tough to do. But if you have you and your buddy, so 2 people moving it, not so bad, right? If you have 3 or 4 people moving it, now it's really easy, stuff like that. And so this is the same case, right? So you have more than just the 1 atom being able to take that charge, the better. Okay. So with that, the other thing is when the resonance stabilization is large is when the resonance structures are equivalent to each other. So here for benzene, stuff like that, and so these are equivalent to each other. They both have the same amount of nothing with charge. Everybody octets filled. Everybody has the most bonds. That provides a massive amount of stability. And so benzene, you've got these electrons delocalized around here. This is incredibly stable. And we'll talk about this. This is called aromaticity. We'll talk about that later in the book. So with that, so all things being equal, general rule of thumb, more resonance structure means more stable. The structure is more stable. So it can either be this is how it wants to be, or if something happens and it has to bear a charge. So with that, so the more resonance structures it can do to help stabilize it, the more likely that reaction is to happen. Okay. So again, atoms can't move. I get out a number of the so with that, so atoms can't move. So here, notice how a hydrogen here, right? It's just the bond that moved. Here, this hydrogen moved over to this carbon, right? So now it's got 2 carbons on it. So this is a different isomer with that. So these are resonance structure. This is an isomer. Okay. Now arrows in this course have meanings. Okay. So if you're talking about a straight arrow, you're talking about like a reaction occurred. Okay. So either a single-headed arrow means just a reaction occurred, or something like, two opposite arrows on top of each other. That's an equilibrium. Now a double-headed arrow, that would be between resonance structures here, right? So you see it here. So you're interconverting between resonance structures. But a curved arrow means that electrons are moving around. Okay, so if you have a double barbed arrow like this, so if you notice the two barbs right there, that means two electrons are moving around. If it's a single electron moving, then it's just a single barb. So like that. And so these arrows do in fact mean different things. Like that. So, and if you looked closely, when we talked about the lithium fluoride, when it showed that the electron was moving from the sodium to the fluorine, it was just a single barbed arrow that was moving because it was just one electron. Now, 95% of the time, we're going to be dealing with just two electron movements, and so we're going to be using this double barbed arrow, stuff like that. But we'll every once in a while look at that single barbed. Like that. So drawing resonance structures. So when you show the curve, you're going to want to go from the negative to the positive, right? So think about how you're giving directions to those electrons for how they move, stuff like that. And so to be eligible to be able to participate in the resonance structures, you have to follow 3 rules. You have to satisfy just one of the requirements. It either needs to have a charge, it needs to have a set of lone pairs, or it needs to be part of a double or triple bond. So it needs to have either a p orbital. In technical terms, you either need to have a free p orbital, or you need to have a pi. So that's a free. You need to have a free orbital, basically, either a hybrid orbital or a p orbital or pi orbital, something like that. Okay, and so here, so how do you know when you're done? That's the classic question. Well, you've either one of two things have happened. Either you've run out of possible possible resonance to use, or possible atoms to use, or you've come to the end of the chain, or if you have a cyclic structure where it's a ring, so like that, so you come back to where you started, and then you're done. Okay, so here, so this is going to have a positive charge, so like that. So here, this nitrogen, what it really wants to have is a set of lone pairs, 4 bonds, right? So with that, this nitrogen here. This oxygen here has 3 lone pairs and a bond. What it really wants to do is it really wants to have 2 sets of lone pairs and 2 bonds. And so what it can do is these electrons are going to get attracted to here, and so it's going to want to lay these down. So, but the problem is this nitrogen can't have a 5th bond because it already has 1, 2, 3, 4. It can't have this 5th one coming down. So what it has to do is it moves electrons, and usually what you're going to do is you remove. You can't break a sigma bond here, but you can break a pi bond. You can move the electrons in a double bond, so you can move these up to that oxygen to make this. All right. So now, right. So they already have these 2 2 lone pairs, but now these 2 electrons here end up making this 3rd lone pair here. Now we haven't done anything with this, and so that's okay. Right, so we've already used this oxygen, that oxygen. We've used that nitrogen too, but we haven't done anything with this one. So let's say this one can come in, move one of its set of lone pairs down, right? So it can have 2 bonds and 2 lone pairs. But again, this nitrogen can't. Oh, there should be a positive charge there. This nitrogen can have 5 bonds, so it's got to get rid of 1, and so it pushes the electrons from that double bond up onto that oxygen, and so now you've got this. Right? Okay, and so now it looks like this, and so now you've used all of your eligible atoms at least once, and so you're done with that. And so this is a positive charge here, right? And there's no negative charge there. With that, and so there you go. Now you say, well, aren't these just the same and just rotated it? Well, no. Because if you were to measure these bonds, these bond distances, you wouldn't see single, double. What you'd see is, if you actually measure these, all of these bonds would be the same length. So like that, they'd be 1 1/3, 1 1/3, 1 1/3 length. So if this was 100, what is it? if this was 130 and this was 100, right, this would be 110, 100. What you would actually see would be 110, 110, 110. So so that's what it takes into account. Okay, so for quantum mechanics, we're not going to talk that much about quantum mechanics. But one of the things you want to see is because we're going to talk about hybridization of how these atoms are put together. So what's happening is you have what's called constructive interference and destructive interference. Some of that. And so when we're talking about these these orbitals here where electrons are, we're not talking about positive and negative charges. What we're talking about is plus and minus mathematical values, right? And so if you have two positives adding together, you get an even bigger positive number. If you have two negatives adding together, you're going to have an even bigger negative number. But the problem is if you have a positive and negative adding together, they're going to destruct. And so you either get additive or constructive interference or destructive. Okay? And so that's what's happening here. So we can use these with these orbitals. And so first thing we have are these atomic orbitals. So we have the s orbital, we have the p orbital, which is sort of dumbbell shaped, and you have the d orbital. We're not going to talk too much about d orbitals. There's also f orbitals as well, but we definitely don't deal with those. We barely talk about d. So for the s and p orbitals are what we deal with 99.9% of the time in this course. So, so the s orbitals you can have, they just accommodate 2 electrons. The p orbitals will accommodate 6. The d orbitals will accommodate 10. Something like that. And so the way that you fill these up is these. If these can fill 2, you get 2. So that, and then the next, so you go up, and then the p, s, p, d, things like that. So so the way that you can either memorize that, or you can something like that. So when you talk about the p orbitals, so the way that we get these 6 in here is we put like an electron here, so about that, and so they can go either in this along the x-axis, along the y-axis, or along the z-axis. You can have a dumbbell in each of the 3 axes, and remember, so like this is the positive, and that's the negative. This space in between them, something like that, where there's no electron density, that's called the node. So, okay. So the way that you can start filling these, right, so we're going to look at the lowest orbitals first, and so 1s, 2s, 2p, 3s. You can either memorize that, or you can look on the periodic table. So this is an s, right, because there's only 2 electrons, and then 2s, and then 2p. So the first type of orbital you come to is an s, so it starts with 1. The second type of orbital you come to is p, and so you start with 2p. And you go across here, and you come across here, and then now we're in this block. So and so now d is the third type of orbital you come to, and so now it's 3d. So for that, I always remember like 3D movies and stuff like that. So and then 4p, things like that. And if you were to keep going, you then come down to the f block, and again that's the 4th type. So it starts with f. And you want to know how many electrons are in. You can accommodate. You can just count over, right? So s orbitals can take 1, 2. Right, so with that, so p orbitals can take 1, 2, 3, 4, 5, 6. D orbitals can take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F orbitals can accommodate 14. Notice how they are, so 1 plus 1, 3 plus 3, 5 plus 5, 7 plus 7. So, yep. For that, so the Pauli exclusion principle is so each orbital type, they can accept 2 electrons per orbital. So like for the s orbital, there's only you're going to be filling it 2 electrons, so there's only 1 orbital type. For the p orbitals, we need 3 orbital types because that's how we get the 6. We can accommodate 6, so like that. And so you can do for the p, there's 3 different orbital types. Okay, if they're paired up, they're going to have opposite spins if paired up. Okay, so Hund's rule is the fact that they're antisocial, so they'd rather fill up singly than doubly. That's why I did the 1, 2, 3, 4, because they'd rather fill up singly and then double up. Okay, because you're trying to put two negative charges together. It's not always good, right? Something like that. So if you look at sulfur, right? So these are something like that. So they're all coming across here, 3s, and then you go 1, 2, 3, and then you fill up. Put the fourth one in there, right? Because these are the valence electrons. 1, 2, 3, 4, 5, 6. Okay, so these are the core electrons. This is what's looking on this. This is the same configuration for neon, stuff like that. And then these are the valence electrons. Okay, so the problem with atomic orbitals is they can't handle covalent bonds and stuff like that. And so what we're actually using are what are called molecular orbitals. And this is where two atomic orbitals are overlapping, and they're called linear combinations of atomic orbitals, LCAOs. And so what's happening is you can have two different types. You can either have, say, two. So when you combine these two atomic orbitals, you can either have like a plus and a plus to come together, and you make a what's called a bonding, which is a sigma bond here, or you can make a sigma star or anti-bonding if you had a plus and a negative, right? So you would destruct, and so you get an anti-bonding. You'd have a node right here, stuff like that. And so this is two. So if you have two s orbitals coming together, it's called a sigma bond because the Greek letter for s is sigma. So it's a lowercase sigma. Stuff like that. And so if you can have bonding, stuff like that. And so that's where you have like plus and plus coming together, and they're additive. So that's the lowest energy. The anti-bonding molecular orbitals, those are the antibond. The antibodies are the high energy atomic orbitals because it takes a lot of energy to make this. With that, and so you can also have non-bonding molecular orbitals. That's where you shove all the lone pairs, stuff like that. So they're just kind of not really participating in anything. Stuff like that. So, but when you're combining these things, remember we have to be conservative about this. How many atomic orbitals go in is the same number of molecular orbitals that come out. Half of them will be, usually half of them are going to be bonding, the other half are going to be anti-bonding. And so what's going to happen is you're going to have the lowest occupied molecular orbital, which is in this case is your bonding, and then the lowest unoccupied molecular orbital here, which in this case is the anti-bonding, stuff like that. So the HOMO and LUMO, stuff like that. So, and a sigma bond is between two s orbitals, with that. So, okay. So how do you account for the bond angles? Well, if you cross the two different types, so let's say you have an s, so plus, let's say a plus s and a minus p. What's going to happen is you're going to have this side be additive, this side be destructive, and so this is going to be really tiny, and this side is going to be ballooned out. Same thing here. If you mixed it the other way, where the plus was on this side would get ballooned out, and this side would get would shrink. Okay, so you get a little bump over on this side, and so we're going to put in, so we would put in this case we have, we put in two molecular orbitals or two atomic orbitals, and we get two molecular orbitals out. Okay, so if we're going to mix S and P, so with that, so we're going to get this one, right? So we have we put in an S and a P, so there's two atomic orbitals, so we need two molecular orbitals out. We get one SP on this side, one SP on this side, and what we'll do is we'll just stick an electron here and an electron there. Okay, now the other two sets of p orbitals here, this one, the Y and the Z, we're not going to be messing with it. They're still just regular p orbitals. Okay, so, and you can either have those hybrid orbitals, the sp orbital would be like this, or along the z-axis, depending on however you need it. Okay, so like that. So if you were to combine an s and two p's, what you would do is, right, your three atomic orbitals out. So by that you're going to get three molecular orbitals out. So you have a lobe here, and a lobe here. You're going to stick an electron in each one of those. So by that, and then you got an unhybridized p orbital that you can use for other things. Right. So by that, notice how this is 180 degrees apart. Notice how this bond is 180 degrees between these two hybrids. Okay. So for the if you were to mix all four atomic orbitals in it, the s and the three of the p's, you would end up, four atomic in, four molecular out, right? So the way that you space yourself is like this, and so you got the bond angle is 109.5 degrees apart. It's your tetrahedron, which accounts for the shape. Okay, so you would say stick an electron into each one of those lobes. So like that, and so for the SP, right? So it looks like this. There's one hybrid lobe over here, one hybrid lobe over there, and so there's 180 degrees between those lobes. 120 in the SP2, which is exactly what we see, the trigonoplanar. 109.5 for the tetrahedron for the SP3. So this explains the VSEPR modeling, stuff like that you would have seen in general chemistry, stuff like that. And so for valence-Von theory, so what about molecules beyond H2, stuff like that. So we use this valence bond theory. What you're saying is that atoms bonded to two or more atoms, they have hybrid orbitals. But again, you're only using these valence electrons. New orbitals the new orbitals are produced by mixing two atomic orbitals at a time. One from each adjacent atom, and usually stick one electron in each lobe, unless it's a lone pair, and then it's a non-bonding. And so here you're going to stick. So for here you've got ethane. For that, so you have an electron here into each one of these purple lobes, and then it's going to be mixing with this with the s orbital from the hydrogen, right? So one electron here, one electron here. There you go. You got your bond. It's each one here. You can also have one electron in this hybrid, one electron in this hybrid, and then so you have a 2-electron bond here, which is this carbon-carbon bond. So with that, and so there you go. So if you have a sigma bond, it can either be between two s orbitals, an s and a hybrid, or two hybrids. Those are going to be your s orbitals. For each bonding, you are going to have an antibonding, stuff like that, and so you're going to have these two together are. When you make bonding orbitals, they're going to be in lower in energy, but you're also going to you pay the price of also making an anti-sigma bond, stuff like that. So you also have an antibonding. This is an antibond molecular orbital, stuff like that. So version as well. So if you want, because we know, so that's how we account for single bonds. But we can also have double bonds, and so what happens is you've got these hybrid orbitals here, electron, 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 but you still have this p orbital that you haven't done anything with. It's got an electron that's swirling between these two lobes, stuff like that. So if it comes into contact with these with the p orbital over here, stuff like that, so you can have a bond or an electron here, an electron here, and if they come together, say like this, right? So they're in the same plane, they can come in and you can get electron density overlap, and so now you can stick two additional electrons in here, and so now you've got 4 electrons in between these two carbons, so now you get 2 bonds. So this is called a pi bond because you're overlapping to p orbital. Pi is the Greek letter for p, so like that. So there's a pi bond, and so the first bond that gets formed is always going to be a sigma bond. Any bond after that between those two atoms are going to be pi bonds. So stuff like that. So you can either get constructive overlap to make the bond, you can get destructive overlap to make the antibond, stuff like that. And so because this overlap, it's not great, stuff like that. It's a little bit less stabilized than a sigma bond, and so this pi bond is going to be a little bit less energy, which means the antibonding isn't quite as destabilized, stuff like that. And so the more energy you get stabilized out, the higher the antibonding and stuff like that. And so this is in the middle of that. So the reason for that is you've got, for the sigma bond, you're getting really extensive overlap, and so you get a lot of really nice interactions between the two. So for the pi orbitals, what's happening is you've got these two lobes, and the overlap just isn't quite as strong, and so you don't get quite as much stabilization out at the end, stuff like that. So now, if you want to stick these hybrid orbitals, if you something like formaldehyde here, if you have to stick those lone pairs in somewhere, and so what you do is you stick a lone pair into this lobe and a lone pair into that lobe. They have their 2 electrons. The lobe has its 2 electrons in there. It's fine. And so there's no overlap. So they're called non-bonding, and so they end up just being normal. There's no energy stabilization for there because there's no overlap. So for triple bonds, what you do is you just do that pi overlap twice, and so you have your hybrid. So you have electron here, put an electron into this p orbital, into the blue p orbital, and then an electron into this green p orbital. So by that, and so the greens can overlap, right, and the blues can overlap. So there's 2 electrons from the greens, 2 electrons total in the blues, and then an electron, 1 electron from each one of these purples. So now it's 6 electrons between those carbons, and so each bond has 2 electrons. So now you got 3 bonds. So you got acetylene here. Okay. So again, you're going to have bonding and antibonding. Okay. So if you want to count the number of sigma and pi bonds, so like that, and so you can count this, right? So the first one is sigma, and so sigma pi pi right, on this one. So it's 1 sigma 2 pi. Here you've got this bond here. It's just sigma and no additional bonds. So that would be 0 pi. And so over here, the double bond, the first one's a sigma, and the rest one is pi. So 1 sigma, 1 pi. So if you notice, there's always 1 sigma, and then each additional bond is going to be a pi bond. So that's how you look at this. Okay, so determining hybridization. So is what you do is so the hybridization. Okay, so it's bond sets plus lone pair sets. Okay, and so for here, double, triple, single, double, and triple bonds all count as 1 set. Okay, so if you're looking at, and you're looking at this here, right? So if you look at that first one, right? So you look at this right there, right? It has 1, 2, 3, 4 bond sets plus 0 lone pairs. So that means it has. We get out 4, so that means we're going to need 4 letters. So the first one is always going to be S, and the next ones are going to be P, P, P. Okay, so that means this is an sp3 hybrid. For this next one, right, so it's actually like this. Okay, we have 1, 2, 3 bond sets plus no lone pairs. Okay, so we need 3 letters. So it ends up being S, P, P, right? So you start with S and then add P's on there. So now this is sp2. Okay, so for this one down here, right? So if we're interested in that oxygen, right? So we have 2 bond sets plus 2 lone pairs sets. So you have 4, and so you're going to get S, P, 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 sp3. So there you go. So if we're looking at this one here, this oxygen here, we have 2 lone pair sets, 1 bond set, right? A double bond is just considered 1 set. So 1, 2, 3. We need 3 letters, so it's going to be sp2. So spp. So sp2. This one here, we have 1, 2, 3 bond sets. So stuff like that. So spp. So this is also sp2. Here, for this carbon here, we have 1, 2 bond sets, no lone pairs, so it's going to be sp. So it's sp1. So this is sp2, sp2, sp3. Or excuse me, sp. Okay, so for bond rotation, right? Stuff like that. So you can get free rotation around the just a plain sigma bond, because when it rotates, it doesn't affect the overlap. Stuff like that. But for p orbitals, because they're in a plane, if you're to rotate just one of those bonds, what's happening is you have to break that pi bond, and so pi bonds do not turn. They cannot rotate. Stuff like that. So you're not going to be able to get this around any sigma bond. Any single bond, you can get rotation. Double bonds, they're locked into place. And for double bonds, right, so like that. So these bonds are all going to be 120 degrees, so like that. And so these bonds that are in orange here, those are locked into place. Now you can get these methyl group or this hydrogens here and that carbon. Now the carbon can turn, so that you can get rotation around that around this bond here, but that carbon is locked into place. So like that. So they just kind of spin, stuff like that. So okay, because there's no rotation, it actually makes a difference about how those atoms are oriented. So in this case, so if we talk about cis, so that means that like in this case, so I usually look at the hydrogens. The hydrogens are on the same side, here, here, and here. They're both facing down. So like that, and so that's cis, so down, down, so that, or up, up. So like that, for the trans, you've got 1 up, 1 down. So Like that. So, and they're going to be different sides. So this is the trans version and cis version. And so if you notice, even though it has the same they're isomers, they're even connected very similarly. They have different boiling points. Okay? Stuff like that. So you see this with cis and trans. So this is having a double bond. We usually call that being unsaturated. So if you have a saturated fat, what's happened is you have just single bonds, carbon-carbon single bonds, but if it's unsaturated, it's a double bond, and there's actually a kink in here, and this is actually a cis double bond because notice those hydrogens are on the same side. If you have a monounsaturated fat, stuff like that, so what's happened is you have a single alkene in your chain. If you have polyunsaturated, you have multiple cis double bonds in here. When you get a trans, when you talk about trans fat, so that what's happened is as you convert chemically going from this to this, sometimes the reaction goes a little squirrely, and so it goes back to a double bond. But because the trans is more stable, it won't do the cis; it goes to the trans version. So there'll be a little. So when you do the hydrogenation with oil to make to go from the soybean oil to Crisco, so by that, so what's going to happen is sometimes a little bit of that's going to get turned into this. So, that. So your body knows how to deal with these two, so that's why they can get metabolism. Although this is pretty slow, so by that, so this can accumulate. But this here, the trans, it doesn't know how to handle that, so it can't metabolize it because it's just not found in nature very often. Stuff like that. And so the other thing is the increasing bond strength. So being able to break the bond, just take it and rip it apart, the more bonds you have in here, triple bond, it's going to be more difficult. Stuff like that. And so it's just, it's the parable of the sticks. If you have one stick, you can break it, but if you have 3 sticks, it's going to be a lot harder to break it. Now, this does not mean unreactive. So breaking the bond and reacting, 2 totally different things. Stuff like that. So, but as you get more bonds in there, the bond actually shrinks. So a carbon-carbon double bond is the longest. A carbon-carbon triple bond is the shortest. Stuff like that, because they need to sort of move together to make sure that you get good overlap. Stuff like that between the bonds. Okay. The other thing is, as you pack more electrons in there, you're going to get a lot more electron density in here, right? You're putting 2 electrons between these carbons, and 4, and then 6, stuff like that. And so what's happening is you're getting a lot more electron density. It's becoming packing more and more negative charge in there. So okay, good luck.